Good afternoon. My name is Graham Cron. I'm recording this lecture outside of normal lecture hours just because of timing, where we're at with material in the current classes that I'm teaching here down in Fullerton. All right, with that being said, let me transition into talking a little bit about friction. All right, so the forces that we've studied so far, some of which being weight, right, and the normal force. The next class of force to look at is the friction force, right? And the friction force is an incredibly important force because we really can't get away from it in everyday kinds of motion. All right, to give you one example of this, as I pace back and forth across the classroom, it would be impossible for me to do so if my feet and the ground, there weren't a rubbing or a sticking between those two surfaces, right? So when we start talking about friction, we're talking about a contact force. It involves the contact between two surfaces as they rub against one another. And it's not just myself walking back and forth or you walking back and forth, but if I was to try to pick up an object, I rely on friction to grasp it. So I got a 1 kilogram weight here. In order to pick it up, if I was to clasp it on either side of the weight and begin to pick it up, if I don't clasp hard enough, my fingers slide right off, right? If I clasp just hard enough, I can pick this weight up. And obviously I could really grip it really hard, like a vice grip, and lift this weight off the ground. Right, so that contact we see then right away depends on the strength of that contact, which we've been calling our normal force. All right, and a lot of animal life utilize static friction. A lot of geckos, for instance, or other bugs, when they climb vertical surfaces, they rely on van der Waals interactions in order to climb. And the stickiness, right? So let's see here. What I'm going to do is try to quantify this friction force a little more thoroughly here. And to do that, I'm going to use a spring scale. And I'm going to use that spring scale to drag a block across the surface. So let me draw a picture of the setup here on the board. I have the ground. I have a wooden block, and I'm going to drag this block along to the left. So I'm going to pull it to the left with a force F. Right, and let's draw in the other forces that we know that are acting on the block. There's the weight, the force of gravity, pulling the block towards the ground, and then we have our familiar normal force upwards, which acts between the two surfaces. Now, on a microscopic level, these two surfaces aren't completely smooth. So the wood has some graininess to it, has some texture. Same thing with the wooden platform right here. There's some imperfections to it at the microscopic level. Even as you feel it with your fingers, it's not completely smooth. So the surfaces kind of stick together. All right, so if I pull this block to the left, the friction force is going to oppose the direction with which the block is being pulled, and I'll call this the friction force lowercase f. All right, so let's try to measure this friction force a little more quantitatively here. So I got a spring scale which measures force in newtons. Just to convince you here that this is calibrated correctly, what I have is a 1 kilogram weight. So if I hang the 1 kilogram weight from the scale, we see that we get a reading of just under 10 newtons, or closer to 9.8. So this scale is calibrated fairly accurately. Right, now what happens as I attempt to drag the wooden block on the wooden surface with a force scale here. Now, if there was no friction at all, it wouldn't require any force to drag the block. So let's see, pull it along here. All right, well, I don't really measure any force here. Now, is that because there's no friction, or is that because the friction force is just very, very small? So I would put it out to you that it's actually the latter there. So, to see that, let me add some weight to the wooden block. So here I've added 1 kilogram of weight. Now if I attempt to drag the block, if I start pulling on the spring scale, you see even with a non-zero force, the block doesn't want to move. Those two surfaces are sticking together. And then, okay, right around 4.5 newtons, I can start to provide just enough force to drag that block along. What would happen if I doubled the weight, added another kilogram onto the block? Well, let me start slowly increasing the force. All right, slowly increasing, and it's just over 8 newtons, just around 8 newtons, when there's enough pull force to actually cause the block to move. All right, so what does that tell us about friction? Well, it tells us, first of all, it tells us that there is friction, right? If there was no friction, any arbitrary force would cause the block to move, right? But the more weight that the block has, the larger the normal force is, and the more friction there is. All right, so the first kind of friction that we're going to talk about is called static friction. And static friction, which lowercase f subscript s, is less than or equal to mu s, which this quantity right here we call the coefficient of static friction, times the normal force, n. All right, let's look at a couple features of this equation. Why do I have, first of all, why do I have the less than or equal to sign? Right, the reason for that is because the only time the static friction will be equal to mu Sn is when is the maximum amount of force you can apply before the block starts to move. Right, but as I connect the spring scale here to this mass, right, I don't have to apply 8 newtons. I could apply only 4, 4.5, 5, 6, and it's only when I get to 8, though, do we actually see motion in the block. All right. So the maximum friction would be equal to mu Sn, and we see here friction itself is a contact force. So this quantity, which we're introduced to here, mu s, is really a measure of what I'll call the stickiness between two surfaces. Right, at the microscopic level, there are intermolecular bonds that are being formed between the two surfaces. Now, the exact microscopic description of that mu coefficient is going to be very, very complicated, right? It's going to depend on complicated forces like the van der Waals interaction, and due to surface irregularities as well. Like as I mentioned earlier, no surface on the microscopic level is perfectly smooth, so we'd expect there to be some roughness, right, when surfaces are in contact with one another. Now, second important point is, why do we call it static? Well, we call it static friction because there's no relative motion between the two surfaces. All right, now one of the questions I want to put forward to you as a class here is, what might we do, how might we measure the coefficient of static friction? This is going to be a friction, this is going to be a parameter that depends on the two surfaces that we're looking at. So for instance, in my setup right here, I'm looking at the coefficient of static friction between wood and wood, right? So how might we actually measure, experimentally go out and measure how sticky those two surfaces are, right? And that's going to be very important for engineers to know when you're designing tread on rubber for a car driving down the road. You want to know at what point would the rubber begin to slip against either the concrete or the asphalt, as one example here. All right, so I already posed one way. Write the question up here: how might one measure μs? All right, based on the demonstration that I've done here, we could reason that there's a way to measure μs just by taking the ratio of Fs and N, right? So number one, drag a block with a spring scale. And then we would just take the ratio of the force that we measure on the spring scale, which would be equal to the static friction force. Oh, this is I would take the ratio of the force that I apply, divide that by the normal force, which is going to be equal to the weight of the object on a flat surface. All right, so we could calculate the μs using a method such as this, and that will be one of your homework problems to complete before next class. All right, what's possibly another way to measure the coefficient of static friction? And that's one that I'm just going to set up here and then have you complete this before next class. All right, another way to measure μs is to measure the angle at which a block slips on an incline. So I'll call this the angle of slip on a tilted plane. All right, so what do I mean by this? Well, if I take this incline, if I take this wooden block right here, and I begin to set it on an incline, slowly increasing the angle, I reach a point where the block starts to slide down. You can kind of see the block slowly starting to slide down. Right now, we can actually, just by measuring that tilt angle, determine the coefficient of static friction. So this is going to be a homework problem, but let me give you a hint here. This angle is independent of the normal force. So if I take off 1 kilogram of weight, that means that the angle with which the block slips should be the same, if my claim is in fact correct. All right, you kind of see that to be true. The block slides down at the same angle here. Let me try that one more time here. All right, the block is slowly starting to slide. So it's the minimum angle before the block starts to slip. What if I take off another 1 kilogram and just look at the block itself? Is there going to be a radical change in the angle? All right, I got to kind of, you see here, I'm actually kind of giving the plane a little bit of a shake, just to kind of get it set in motion here. So 2 different ways to measure the stickiness between the two surfaces, in our case, the wood on wood. All right, so for next class, I want you to construct a free body diagram for a block sliding down an incline and calculate the coefficient of static friction only dependent on the tilt angle. All right, I'll see you all next class.